So in this section, we are going to continue with our simple self-attention mechanism. The subtitle here, or the section title, is a simple self-attention mechanism without trainable weights, because we are still talking about a simple self-attention mechanism. In later videos, we will be introducing trainable weights that help the model optimize the computations. But here we are still talking about the simple self-attention mechanism that we introduced in the previous section. Now, we are going to generalize this a bit more now, because in the previous section, what we did is we focused only on one of the inputs as the query, and then computed the attention weights between the query and all the other values, all the other inputs. And then we computed the so-called context vector with respect to the second input query, which is why you can see the 2 here. That's the second query. So this is the context vector with respect to the second query. Nonetheless, it contains information about all the other inputs. So now we are going to generalize that. Again, in the previous section, I want to make this crystal clear so it's a bit more, I think, intuitive to understand what we are doing here. In the previous section, we computed the attention weights only with respect to this second input vector. Now we are going to compute all the other input attention weights here. You can see this is a 6 by 6 matrix, because it's for each input. We have 6 inputs. We compute the attention weight for each other input. And that's why it's called self-attention, because it's with respect to the input sequence itself. Okay, so let's actually do this by borrowing some of the code from the previous section. So we need to first, so this was the computation of the context vector, which involved the attention weights. So we have to first compute these attention weights. So here, let's borrow this one. And what we've done in the previous section is we computed it with respect to the second input token, like I mentioned. Now we are going to generalize this. So let me just get rid of some of the code comments, and it might be a bit easier to read. So what we have is we have an iteration over the inputs, and then we compute these attention scores. Now, let's actually modify this a bit. So let's make this a bit more general. So instead of saying input query, let's say xj. And then instead of saying attention scores with respect to the second input token, let's just call that attention scores, and then do ij. So this will be now a matrix. A matrix, this will be the matrix. This is a specific value. But so we have now a matrix attention scores that has the shape 6 by 6. And if I write ij, this would be a specific value in this attention matrix. So we have this 6 by 6 attention score matrix. So let's actually initialize that. So for that, we are going to use torch mt 6, 6. So this is our 6 by 6 matrix. And then what we are going to do is, let's get rid of this because this is only for the second row, right? So we want to do it for all the rows. Now we are going to compute these values here, where each ij is each cell here. So what we are missing is we're missing one for loop. So what we have to do here is we have to do for j xj in enumerate. And then we indent this and have it like this. So what we have here now is we have a double for loop. And we are computing now the dot product between each input and each input. So xi and xj, if we iterate like this, it will be this one, 0, 0, then 0, 1, 0, 2, 0, 3, and then 1, 1, 1, 2, 1, 3, and so forth. So it's going to be iterating over this whole matrix, the 6 by 6 matrix, via this I and j here. So if I do it like this, this would be then our matrix here. So this matrix. Now, the values look a bit different. You can see it's 0.2, we have 0.9 and so forth. And this is because these are the attention scores. They are not normalized yet. So we have to also apply the softmax normalization, and we will get there in a moment. So I wanted to show you one trick though. So this is how we do it manually using dot products, but there's a concept called matrix multiplication. And we can actually, instead of doing 2 for loops, we could do a matrix multiplication, which is much faster, because in PyTorch, for loops are actually quite slow because they can't really be optimized that much compared to matrix multiplications, which have very efficient implementations on the computer. So we can actually compute this same thing here by doing a matrix multiplication. So if you're not familiar with matrix multiplications, it is, I would say, a topic for a separate video, perhaps. But yeah, I don't want to make these videos too long, because then we would end up doing a whole course on deep neural networks and linear algebra, and then 3 weeks later we'll get to the self-attention mechanism. So if you're not familiar with matrix multiplication, I would say this is essentially an automated or shortcut way of doing these 2 nested for loops. And you can see, if I didn't make a mistake here, we should get the same values. So you can see these are exactly the same values. We are just automating this now. So these values here, they do look different though from these here, which are the attention weights. So what we forgot is we forgot the softmax. So we computed previously this softmax. So that is what we are going to do now. So let's do the softmax. So attention scores, it's a convention. Attention scores refer to the unnormalized values, and then we can do attention weights and normalize them. So like this. Let's print them. And so these are the normalized weights. So you noticed I did type something like dim1 here. So what does that mean? So it's essentially so that the weights along this axis sum up to 1, I hope. So actually let's take this one and do a torch.sum. Must be a tensor, not a list. Oh yeah. So 999, okay, let's try another one. One too many. Yeah, they do some minus rounding errors. They do should sum up to 1. So we could also actually do this automatically instead of testing all of them. We can do attention weights dot sum dim minus 1. So you can see they do sum up to 1. So each of them basically. And if you paid close attention, let's see, I actually didn't. So let's see, previously in the previous section, we computed these attention weights with respect to the second input. So this is with respect to the second input. So this here should technically match what we have here. And as you can see, oops, let's just do it like this. So as you can see, this one matches this one. Now what we have done is we have automated this one. So we have automated this whole computation here with this attention weight and everything in a few lines of code. So technically the only 2 lines of code we have is computing the attention scores and then the attention weights. So we have everything in 2 lines of code that we have done previously in the previous video with a lot of work for one of them. Now we have it for all of them. So that is how we generalize things. We are missing one thing though. If I go back, we computed the context vector after the attention weight. So that is still something we have to do. So how do we do that? How do we compute the context vectors? Again, there's a handy way of doing that with matrix multiplication. So I can type context vex and then the attention weights, then matrix multiplication with all the inputs. So instead, so this is generalizing what we had in the previous section. This is generalizing this computation. But if we do it manually, we have to have 4 for loops. We have to have one for loop over the inputs, compute the attention weights, and then we have another for loop for computing those weighted sums, and then we have to do it for all the vectors, and it's a lot of for loops. So here we just do matrix multiplication for the attention weights, another matrix multiplication for context vectors, and then we are done. So this is it. So we are done. And yeah, again, if you paid close attention, this one should resemble the context vector we got in the previous section. So let's see, where is it? Here. So this is context vector 2. Let me just copy the values here and paste them below. And yeah, we can see those are indeed the same. But now we have done it for all the other ones too. So by swapping out what is our query. And yeah, so this is how we make things nice and compact. So we have now, if I clean this up a bit, we have now very few lines of code. Very few lines of code to compute the attention weights and then the context vectors. So I can do it like this. And then you can see this is all we need to compute the context vectors for our simple attention mechanism. Yep, so we have now these for all the different inputs.
Get this book at Manning.com.